If quantum mechanics hasn't profoundly shocked you, then you haven't understood it yet. Niels Bohr. According to Newton's mechanic, the physical world was a deterministic machine, where the past defined the future. This too deterministic approach was true, until Einstein appeared on the scene. This approach was dominant until Einstein. A new understanding was born where nothing is as it seems, everything fluctuates, vibrates, and uncertainty prevails. The quantum world is certainly not like the predictable universe of Newtonian physics. Advances in physics in the early 20th century not only changed the laws of physics, but also destroyed much of the epistemological foundations of classical science and philosophy. Quantum mechanics caused a great surprise to anyone who understood it. In fact, those who do not understand it are otherwise surprised. The quantum world is powerful enough to surprise even those who do not understand it. The world at the quantum level is a world of possibilities and uncertainty and fluctuations. Physicists use the billiard table analogy to express the physical world of particles colliding and interacting in quantum physics. Think there is an impure pool table with no friction, the white ball is quickly sent to the triangular balls. What happens after that is too complex and unpredictable to be followed. Because, the small differences between the starting positions of the balls and their velocity gets bigger with each collision, such that even the smallest collisions will have completely different results. This is called chaos. It is a feature of nature seen everywhere. It is impossible to repeat a game of pool so that all balls move the same speed and position. This requires almost infinite precision. In classical physics, that means according to pre-quantum physics, balls follow precisely certain movements, and if we know the starting position and speed of the motion with infinite precision, the results are predictable. But it has been revealed by quantum mechanics that this cannot be true, so the future is unpredictable. According to quantum mechanics, the game of billiards is unpredictable, no matter how sensitive one moves. Why is that? Why can't we predict the future from the starting positions and speed information? The answer is in the Heisenberg uncertainty principle. To knowing the correct location of the ball, to get a precise image, we need to hit the ball with high-energy photons, but this will significantly change the result of subsequent velocity measurements, so measuring will change the speed we are trying to measure. This makes it impossible to measure both position and speed with infinite precision. Heisenberg's uncertainty principle is that, we cannot measure both the velocity and the position of a particle at the same time, so we cannot know where it is. The particle we cannot be sure of where, can be anywhere. The Heisenberg uncertainty principle is one of the cornerstones of quantum mechanics. Let's have a look at the famous thought experiment, Schrödinger's cat. A cat is placed in a steel chamber with the following hellish contraption. In a Geiger counter, a tiny amount of a radioactive substance, so that maybe within an hour one of the atoms decays, but equally probable is that no atom decays. So, there is a half chance that an atom of the substances decays and causes the Geiger to tick over the hour duration of the experiment. One decays, the counter triggers a little hammer which breaks a container of cyanide. If the atom decays over the hour, the cat is killed. If it doesn't, the cat survives. Treating the box and the cat as a quantum system, how would we describe its wave function? The wave function of the system now exists in a superposition of the individual wave function that describes the cat as being alive, and the one that declares it dead. According to the rules of quantum physics, the cat is currently both dead and alive. One of the strangeness of the quantum universe occurs in the double slit experiment. Make two parallel vertical slits in a metal plate through which light can pass. Let's close the left one of the slits and let's light. After enough time has passed, a horizontal broadband blackening occurs on the film. This dim is the blurry image of the slit on the right through which the light passes. Let's close the right one and open the left one. This time, a second blackout appears that partially overlaps with the first image. Now let's apply the experiment by renewing the film and leaving the two slits open. The figure that appears is not the sum of the previous two highlights. Instead of two fuzzy bands, a series of dark and light bands similar to zebra stripes are formed. The light passing through the right and left slits somehow cancelled each other in some areas. This is a known property of waves. But the most interesting aspect of this experiment is that if there is an observer system that monitors which slit the photon will pass through, the photon acts like a particle again, not like a wave, forming two slit lines. A particle's wave or particle nature is most likely undefined until a measurement is made. The other less likely option would be that of backward causation, that the particle somehow has information from the future, but this involves sending a message faster than light, which is forbidden by the rules of relativity. The situation is not about observing with conscious mind, it is about measuring. The measuring affects the result. Physicists have found that even passive observation of quantum phenomena can actually change the measured result. Despite the observer in this experiment being an electronic detector, possibly due to the assumption that the word observer implies a person, its results have led to the popular belief that a conscious mind can directly affect reality. The need for the observer to be conscious is not supported by scientific research, and has been pointed out as a misconception rooted in a poor understanding of the quantum mechanics.